7b Dynamics of Circular Motion. 7th November, Centripetal Force. We saw in Section 7a that any object in uniform orbital motion about an axis experiences centripetal acceleration, AC, toward the center of rotation. We also know that acceleration occurs only when unbalanced forces act on a system, and the direction of the acceleration is in the direction of the net force on the system, sigma F. The unbalanced force sum that produces this acceleration is called centripetal force, FC. This is one of several types of center-seeking or central forces. Let us first imagine that a puck-like object on a perfectly frictionless surface is connected by a string to a vertical rod rigidly embedded in the surface so that the puck and string can freely rotate around the rod. The puck is set to rotating around the rod in orbital motion. We may assume that any forces acting parallel to the rod, the axis of rotation, and thus perpendicular to the surface of rotation, cancel out. Therefore, the net force acting on the rotating puck consists only of the force exerted by the string that causes centripetal acceleration. From this, we can develop the second-law centripetal force equation by substituting the appropriate centripetal terms. Fc equals MAC 7.10. Equation 7.10 would be more useful to find the magnitude of the centripetal force on the puck if we could use easily measurable parameters of the system described above. We can substitute equation 7.3 from the previous section for AC, which gives us the magnitude for Fc. Fc equals Mac equals M, Vt squared over R, 7.11. Equation 7.11 permits us to use easily measurable quantities to calculate the magnitude of the centripetal force that produces circular motion for a given object under a specific set of circumstances. A string can exert centripetal force through tension, as we'll see in the following example. A planet may exert a centripetal force on a satellite through gravity. See Section 7c. 7.12 Torque. Accelerated linear motion results from a non-zero net force. But what causes accelerated rotation? To answer this question, let us perform some experiments with a playground seesaw. How do you balance a seesaw? If it is empty, you can position the seesaw so that its center is the pivoting point. In this position, the seesaw remains at rest, since half of the seesaw is on either side of the pivot. Each end is attracted to the earth by an equal force. When the pivot is not at the center of the seesaw, the longer side is attracted to the earth with a greater force, and the seesaw rotates. Suppose you place a 25-pound bag of grass seed on one side of a balanced seesaw. What happens? The seesaw rotates, with the weighted side going down. If you place a 25-pound bag on the end of a balanced seesaw and a 51B bag on the end of another identical seesaw, what do you observe? The more heavily weighted seesaw rotates with twice the angular acceleration of the less burdened seesaw. Therefore, you can conclude that angular acceleration is proportional to force. Suppose identical 25-pound bags of seed are placed on two identical balanced seesaws. One bag is placed at an end of one seesaw, and the second bag is placed halfway between the pivot and an end of the other seesaw. You observe that the seesaw with the bag at the end rotates with twice the angular acceleration of the other seesaw. Therefore, angular acceleration is proportional to the force's position vector, r, the distance from the pivot to the place that the force is applied. You can see that angular acceleration is proportional to both the force and the force's position vector. Their product yields the vector quantity called torque, T. It is not possible to multiply two vectors together algebraically since they are not true numbers. However, the magnitude of a torque can be calculated by the formula. Torque equals RF sine theta, 7.12, where ER is the magnitude of the position vector, pointing from the center of rotation to the point at which the force is applied. F is the magnitude of the applied force, and theta is the smallest angle, less than 180 degrees, between vectors R and F when they are positioned tail to tail. The quantity r sin theta is called the moment arm, L, of a torque. C. Figure 7-18 to see the relationship of torque, moment arm, and force. The unit of torque is the Newton meter. You can see from the figure that the magnitude of torque is the product of the component of the position vector that is perpendicular to the applied force, the moment arm, and the force. Maximum torque is obtained from a given force when it is perpendicular to its position vector. If the applied force is parallel to its position vector, the torque is zero. Torque has the same role in rotational motion that force has in linear motion. That is, angular acceleration is produced by unbalanced torques. When the sum of all torques on a system is zero, it will rotate either at a constant angular speed or not at all. The condition of zero net torques is called rotational equilibrium. Mathematically, sigma t equals ONM is the condition for rotational equilibrium, just as Newton's first law established that. Sigma F equals 0 newtons is the condition for translational equilibrium.